We're very happy to have our guest speaker with us tonight. If you only knew it, he has had to make many unusual changes in his plans in order to be here with us at this time. He has considered enough of his responsibility as director of the George C. Marshall Space Flight Center of the National Aeronautics and Space Administration in Huntsville, Alabama, to never accept over 4 major speaking engagements a year. The Marshall Center employs about 7,000 persons and occupies 1,800 acres in the heart of the Redstone Arsenal. Laboratories and engineering buildings and test facilities are valued at approximately $320 million. Dr. von Braun was born in Würzitz, Germany. He has his Bachelor of Science degree in Mechanical Engineering from Berlin Institute of Technology and his PhD in Physics from the University of Berlin. Our speaker has worked with the rocket engines as far back as 1930. Dr. von Braun and a number of his associates began work with the U.S. Government Research and Development in 1945. He and about 80 of his associates and their families received American citizenship in Huntsville, Alabama on April the 14th, 1955. The major activities at the Marshall Center concern the development of NASA's large launch vehicles for space exploration, and personnel at the center performs basic research to develop payloads for space flights and conduct studies of advanced systems for space flight operation. Among the center's current programs is the responsibility for the Orbital Workshop. Under Dr. von Braun's direction, the Marshall Space Flight Center Group has several firsts in space, including the first nose cone of a ballistic missile to re-enter the atmosphere from space, the first primates to journey into space, monkeys Abel and Baker, and the first U.S. Earth satellite, Explorer 1. Dr. von Braun is responsible for the successful launching of Saturn V on this last November 9th, 1967. This is the largest of the U.S. rockets. There will be another launching of Saturn V April the 1st, 1968. Wanted to take time to enumerate a few of the very fine, outstanding awards our speaker has received for his work in rocketry and space research. These include the Distinguished Civilian Service Award from the Secretary of Defense, a citation of merit for contributions toward the advancement of the science of rocket and missile propulsion, the U.S. Chamber of Commerce Award for Great Living Americans, the first honor award of the Nationalities Committee People to People program for patriotic devotion to the country of his adoption, the Distinguished Federal Civilian Service Award presented to him by President Eisenhower, the Hamilton Holt Gold Medal for Distinguished Service to Humanity, the Daughters of American Revolution Americanism Medal, the Alabama Court of Honor Certificate and Plaque from the Exchange Clubs of Alabama, and more recently, the American Society of Mechanical Engineers Man of the Year Award. He's received something like 19 honorary degrees from universities and colleges in the United States and foreign countries, including rather recently one from our neighbor institution, a Doctor of Science degree from Butler University. He is a member of many scientific organizations, including the Indiana Institute of Technology, and is author and co-author of a number of books, including First Man to the Moon, Exploration of Mars, and Careers in Astronautics and Rocketry, and is author of many scientific articles. Dr. von Braun's a pilot in his own right, and it certainly is a privilege for a pilot to be able to introduce another pilot of so many outstanding accomplishments. It's very appropriate that our speaker should help us at Ball State University start our second half-century of development by speaking to us this evening on the second decade of space. Dr. von Braun, we're very pleased to have you here this evening to speak on the second decade of space, and we especially welcome you at this time. Dr. von Braun.
Thank you, Dr. Cooper, President Emmons, students, and members of the faculty, honored guests, ladies and gentlemen. Today is a historic moment in Ball State University's 50 years of service to the community and the nation. And I'm delighted that I could be here to share this occasion with you. I share your pride in the dedication of your new science building. I had an opportunity to walk through about 2 miles of the new building today. I saw every nook and cranny of the chemistry labs, of the physics labs. We went into the planetarium and up to the astronomical observatory. All I can tell you is I've never seen so much science crammed into one building. And I wish I knew 1% of all the wisdom that would be taught in that building. This building will undoubtedly add a strong new capability for multidisciplinary growth to a recognized and respected position of leadership in teaching and research. Search for knowledge is always a noble undertaking, and I envy the students and the professors who will make use of this fine new building to deepen their understanding and enrich their lives. I'm also highly pleased to have the opportunity of joining with so many leaders of government, industry, and education in wishing Ball State University well in the pursuit of the life sciences and all its other activities. In a way, this handsome new structure is a product of the space age, which began a little over 10 years ago. And the achievement of the first decade in space have many of their roots on the college campus. For the science that is to be found on the campus has been merged with the technological might available in American industry and with the management capability provided by the government to give this nation one of the finest periods in its history, the first decade of space. America's entry into space has changed many things. It has changed the beliefs of scientists about the universe. It has influenced the agreements of statesmen in foreign affairs. It has swayed the decisions of industrialists on tremendous transactions and new plans. It has stimulated educators to revise their curricula, and it has even affected the pronouncement of religious leaders. Yes, even the toys of our children have been changed by the space age. Space research has proven a catalyst to the total technological advance of the United States. In attaining the difficult goals established in space, we have undoubtedly gained new knowledge. We have learned new manufacturing processes and techniques. We have developed new materials and products. We have created new industries and provided new jobs. The history of science and technology indicates that a small spring of basic research is often the source of a mighty river of technology. The true worth of any space research project, then, should be judged by its ultimate contribution to human knowledge. Obviously, the judgment can only be made with the benefit of hindsight, by evaluating performance. No one has a crystal ball in which he can foresee the future benefits of a proposal. And the man who sticks his neck out and does so is frequently left holding the bag with its head in it. Speculation on the potential benefits from space made only a few years ago were vague and indefinite. Today they are far more visible, credible, and attractive to users. And yet even now, after a decade of space, it is impossible to make predictions with any degree of certainty and finality. The greatest payoffs, the ones which will be the most revolutionary, the ones with the widest application, may very well come from some unforeseen aspect of a program or from discoveries yet to come. Let me give you an example. 10 years ago, few areas of physics seemed as unpromising from the practical viewpoint as investigations of the interactions between microwaves and gas molecules. And since practical applications could not be foreseen clearly to enter on the balance side of the ledger against expenditures for research, industrial laboratories simply neglected the field, leaving it primarily to university researchers. To the amazement of everyone, this impractical basic research quickly produced the laser and the maser, which are revolutionizing many branches of technology and creating an entirely new and fast-growing industry. Now, if researchers had set out deliberately to achieve three-dimensional photography, something that a laser makes possible, or to improve measurements of distances, another thing you can do beautifully with a laser, or to create a new surgical instrument for the eye, you can weld the retina in your eye to the eyeball with the help of a laser. If any of these other goals that the laser and maser make possible now had been established as the original objectives of all that research, it is extremely doubtful that such indirectly related goals could ever have been reached within the same time frame. It is really the byproduct, if you will, that makes the world go around. And this is not exactly new, nor does it apply to research only. It applies to exploration on the vastest scale. When Christopher Columbus went to Queen Isabella and asked for money for his 3 ships, and she decided to pawn her crown jewels to finance the undertaking, Columbus was telling her that the purpose of the whole undertaking was to improve trade relations between Spain and China. Now ask yourself, has this objective ever been met? Well, you will agree then that it was probably in this case too that it was the byproducts that made the undertaking worthwhile. This business of keeping the cutting edge of progress sharp, probably the most important single task of our space program today, is why we should pursuing the things we are doing. As some of our sister nations have learned from sad experience, you either move with the tide of technological advance or you fall behind on all fronts. For instance, Britain's dramatic change of position in world leadership has been diagnosed as a case of neglected, starving technology. Right after World War II, Britain chose to embark on a program which emphasized economic and social reforms, but she neglected continued technological advancement on a broad front. And now Britain is suffering the consequences of this decision, lacking the broad technological and production base needed to support either continuing economic and social progress and further technological advance. Now today, the United States of America is faced with the same decision that confronted Britain 20 years ago. The question, however, should not be, should we as a nation have space, or should we also concentrate on other things that we seem to understand maybe a little better than the need to go to the moon? But the question is, can we really have the other things, that social progress, the improvement in the cities and so forth, if we curb the technological reach required by things like space exploration, if we allow the cutting edge of our scientific and technological progress to get blunted? That is the question we are confronted with, and I hope we find the right answers and we keep that cutting edge honed. The budget of the National Aeronautics and Space Administration for fiscal year 69 is presently under scrutiny in Congress. This budget, as submitted, and that means long before the appropriations committees have taken their cuts, is a compromise. It's a compromise which NASA fully supports between the absolutely necessary aeronautics and space advances and the need for austerity to reduce inflationary pressures on the economy and to meet the heavy demands on the federal budget of the Vietnam conflict and other pressing national problems. To operate within its framework, NASA, the space agency, is having to cancel some projects, stretch out others, sharply curtail its plans for future activities, and most significantly, reduce personnel. The organization that NASA has created during its first 10 years, staffed with scientific, technological, and managerial talent, is a priceless national asset. Our competence lies in the minds, the experience, and the skills of thousands of highly skilled people. These are the teams that launched the explorers, mariners, rangers, surveyors, syncoms, and other famous spacecraft. And these are also the teams that developed the Saturn launch vehicles, the Apollo spacecraft, and that conducted the Mercury and Gemini projects of manned spaceflight with such brilliant success. Now, NASA does not buy a lot of hardware. Most of its budget goes into salaries and administrative support for people. When funding is reduced, projects must be terminated, and these teams of skilled and trained individuals must be dispersed. Your tremendous asset is gone. To attempt to reconstitute such teams when funds again become available would be outrageously expensive, inefficient, and time-consuming. One of our primary concerns right now is to preserve the strong technological and scientific and managerial base created over the past 10 years so that we may be in a position to continue the exploration of space during the years ahead. The nation's space program is advancing science and technology, and widespread applications are coming closer to fruition every day. The ultimate benefits, we are all absolutely certain of that in NASA, will more than outweigh our investment, expensive as it may seem today, when weighed against other needed expenditures. President Johnson reaffirmed our determination in space when he visited the Manned Spacecraft Center at Houston just 2 weeks ago. Future generations, looking back at our incredible decade, the President said, will be unanimous in their belief that the treasure we have dedicated to sending men to explore the stars was the most significant investment ever made by any people. The nation must stay on its course in its plan to land a man on the moon, the President said. Now I brought a deck of slides along to tell you how we are coming along in this lunar landing program, the Apollo program as we call it. If I can have the first slide, please fasten your seatbelt. Toward the end of the flight, I'll take you on a little round trip to the moon, and if everything works well, we'll even come back. My first slide shows the launch vehicles that are used in our manned space flight program. We started out with a Redstone rocket, a short-range Army ballistic missile that put the Mercury spacecraft in a 200-mile trajectory down the Atlantic range. It was in this configuration that Alan Shepard and the unforgettable Gus Grissom made their rides down the Atlantic. After 2 successful flights with the Redstone Mercury, the Mercury spacecraft was piled on top of an Atlas, also a military intercontinental ballistic missile, much bigger and powerful than the Redstone. And it was in this configuration that John Glenn performed the first orbital flight done on the West. Unfortunately, this flight was also preceded by Soviet accomplishments a few months earlier of orbital flight. There were 4 successful Atlas Mercury orbital flights. The last was conducted by Gordon Cooper and went 22 times around the Earth. Then the Atlas Mercury program was terminated, and a new, larger 2-man spacecraft called Gemini was put on a Titan II intercontinental ballistic rocket, and with this configuration, the Titan II Gemini, 10 successful flights with 2 astronauts in each flight were performed. The longest of these flights was conducted by Colonel Frank Borman and Captain Jim Lovell, and lasted for 2 weeks. With this flight, the Gemini program was then also terminated, and we moved on to Apollo. Now, Apollo is the program to land Americans on the moon before this decade is out. And we have 2 different launch vehicles in this program, the Saturn 1B, sometimes we call it the baby Saturn, compared with this one here, and the Saturn V. Now, the Saturn 1B is powerful enough to put the Apollo spacecraft into an orbit around the Earth and exercise it there, so as to practice all kinds of maneuvers that astronauts will encounter on their voyage to the moon. But it will require the more powerful and heavier and longer Saturn V to give the lunar expedition its first initial push. Here, a well-known lady for comparison scale. Next slide, please. Here's the Saturn 1B after takeoff. The Saturn 1B has 8 engines. In the first stage, you see the white jets coming out. These flames surrounding the jets are exhaust from the turbo pumps that feed the propellants into the combustion chamber. The first stage, which goes up to here, fires kerosene as fuel and liquid oxygen as an oxidizer. The stage burns 120 seconds. At this point, the first stage is jettisoned and the second stage takes over. The second stage of the Saturn 1B is powered by a single engine of 200,000 pound thrust, and it burns liquid hydrogen and liquid oxygen. At cutoff of the second stage, everything, the second stage itself and the spacecraft, which is everything from here on up, is in orbit around the world. 18,000 miles per hour. Next slide, please. Now, the Saturn V is a lot bigger, as I said, and here we are looking into the business end of the first stage of the Saturn V. We assembled the first 4 flight stages of the Saturn V in our Marshall Space Flight Center in Huntsville, where I hang my hat. And so here you see the proud assembly group, the assembly shop on the day of rollout. The shrouds which surround the engines are still not on, but that gives you the advantage that you can see some of the details of the engines here. It is through these 5 big nozzles that the exhaust gas comes spurting out at a speed of about 6,000 feet per second. The thrust is created by millions of molecules flying in this direction, each creating a little recoil like a machine gun, so that the total thrust pushes the rocket in that direction. And clearly, just like a machine gun, a bullet leaving a machine gun wouldn't know whether the machine gun is fired in air or in a vacuum. You get the thrust effect in vacuum just as much as in the atmosphere. In fact, you get a little more. Now, this stage 2 fires kerosene and liquid oxygen as propellants. Total thrust is 7.5 million pounds. Next slide. Here you see this stage fired up on our test stand in Huntsville. The stage fires for 140 seconds. All 5 engines have been fired up here. And what you see here is a display of 150 million horsepower. Our neighbors in Huntsville say that about 1% of that horsepower seems to be converted into noise. At least they came complaining about windows broken and some cracks in the ceilings, whereupon we politely inquired whether they wanted us to move, and they said, "Oh no, please stay." The reason is, of course, that the businessmen know full well that it not only rattles windows but also cash registers. Next slide, please. Well, here, after static testing, the first stage is put on a barge. We talked the Army out of some old barges and put a hangar on. And on these barges that have a simple roll-on, roll-off feature, we carry these stages down the Tennessee and Mississippi River and then across around the tip of Florida to the Kennedy Space Center, from where we launch. The next slide shows the second stage of the Saturn V. This stage is developed, or has been developed, by the North American Rockwell Corporation in Los Angeles under a contract from our Marshall Center in Huntsville. It fires 5 J2 engines burning liquid hydrogen and liquid oxygen. It has the same diameter as the first stage, but much less thrust. It has only 1 million pounds total thrust, made up by 5 of these 200,000 pound engines. This stage has given us a great deal of difficulty because of its rather advanced design and radical new procedures, but it is now behaving very well. For scale, you see a man standing here. Next slide. The third stage of the Saturn V is made up by this thing here. Not this, but this. This stage has a diameter of only 260 inches. In other words, we have now, up on the stack of the first and the second stage, we are necking the vehicle down to a somewhat thinner shape. And this stage is powered by a single engine, just like one of the 5 in the second stage. This stage has been designed and is being assembled by the Douglas Aircraft Company in their Huntington Beach facility in California. This airplane is a converted stratocruiser. It has a real amazing history and is a classical example of enterprising spirit in the best sense of the word. One fine day I got a telephone call, and somebody told me, if you want to see the craziest airplane that you ever looked upon, come out to the strip. It is sitting there. And I came out there, and there was this thing. It looked a bit like this, sitting on the airport, and the guy had just landed. And it turned out this man had bought a surplus Stratocruiser for $26,000 with engines and everything, and had put a great big bubble on top of it because he felt he could make some money by hauling these large stages through the countryside. But he didn't have enough money to go to a complete design of the structure here, so he had simply taken the old Stratocruiser hull and put a kind of a mock-up on top of it. And he said, "I'd like to talk to you." And he said, "Well, I would like to build a real airplane with a real structure here that we can cut up here and put this kind of a load in, but I need $800,000 to do it, and I haven't gotten the money, but I know a banker who is ready to give me the money if you would only promise me that you would sit down and talk to me about a hauling contract if I can produce an FAA certificated airplane here on your ramp." Well, sounded pretty incredible to me to do all this for $800,000. And on the other hand, it occurred to me that there was really nothing to be lost by the thing, because if the man wouldn't get the FAA certification, we wouldn't lose a nickel. But nevertheless, in due respect for headquarters in Washington, I felt this matter was important enough, so I took it to Washington and discussed it there with old, experienced airplane people. And every single one of them told me, "You are completely nuts if you think you will ever get that airplane FAA certificated, and this man will bog down, and then he will ask us for more money, and then we'll have a big argument and so forth, so we advise strongly not to do it. But if you want to go ahead, after all, if you establish quite plainly that we are not assuming any risks in this thing, and it was strictly his problem, there was really no objection. Well, finally, I gave him the go-ahead. Believe it or not, 6 months later, that airplane was sitting in our ramp, and he has now 3 of them, and is making not only a lot of money, but to his greatest joy, he was recently asked by the United States Air Force to fly some supplies to the Far East, because they didn't have an airplane as big as this one. This is, by the way, a very economical way of transporting these heavy cargoes from the West Coast to Florida, because the other way of doing it would be to take it, as we do it with the second stage, by boat through the Panama Canal. And there you're tying up a boat with a crew of 30 people for about a month, round trip time. This plane with a crew of 2 flies from California to Florida in 1 day. So it is actually substantially cheaper than shipping. And since there are no amortization costs involved except the original $26,000 for the surplus Stratocruiser, you can imagine that this is really quite a bargain deal we got. Next slide, please. Now, you cannot simply stack all these stages together and expect them to work as a complete rocket system. So we have set up in our Marshall Center in Huntsville a so-called systems development facility. This is actually a kind of a mock-up where all essential functions in the rocket that involve timing, such as controls of the first, the second, the third stage, the swiveling of the engines, the pressurization of the tanks, are tied together with the help of computers that provide the necessary logic and delay lines and so forth. And we have made thousands of flights in this systems development facility before the first Saturn V ever flew. It's amazing to what an extent you can simulate a flight on such a facility. For example, you can produce an engine out situation at the time when the rocket is just about passing through a jet stream with very high shear loads, and you can measure directly what kind of loads the rocket encounters. You can set up all kinds of failure modes and find out whether any of them are disastrous or can be overridden by redundant equipment. It is like teaching the rocket to fly on a link trainer before you put it in the cockpit, only that there is no pilot, of course, to fly the rocket into orbit. This is done with automated guidance gear. Next slide, please. Well, finally, the stages are mated at Cape Kennedy, and you see here in a composite picture what happens. The first stage, S1C we call it, is put in a vertical position on its launch platform. After it is tied down there, the second stage is piled on top of it, and then the third stage is piled on top of the second one. Finally, this thing here, the instrument unit, a relatively small slice, but loaded down with electronic and precision mechanical equipment, is piled on top of the third stage. And after all this has been completed, we take the so-called Apollo spacecraft, which is really in a way the payload of the Saturn V rocket, and pile it on top of the Saturn V rocket. We'll talk about that spacecraft quite extensively when we go through the mission profile, so let us skip it here for the time being. The next slide. Well, here is actually the command module of the spacecraft in which the three astronauts ride. This is the spacecraft in which we had this terrible accident in February of last year where Gus Grissom, Ed White, and Roger Chaffee lost their lives during what we all thought was a routine test. The spacecraft has been completely reworked, all flammable material has been removed, and all kinds of safety precautions have been taken to evacuate the astronauts quicker than this was possible in the previous design. The next slide shows this changed escape hatch. This hatch can now be opened very quickly from the inside. You see it has a complicated locking gear here, and with this handle here, the astronauts can get out in a hurry. You may ask why such a door wasn't provided from the outset. Well, actually, this is a question of trade-off. You see, in outer space, one of the greatest dangers for the crew is, of course, that you suddenly lose pressure inside the spacecraft, particularly when you're not suited up in a spacesuit, but surrounded by a vacuum. So instinctively, we had always felt anything that opens from the inside out was really far more dangerous than what could happen on the pad. Now, this was a case where we just learned the hard way. Next slide, please. This is another element of the Apollo spacecraft, the so-called lunar module. You see it in the assembly hangar at the Grumman factory in Bethpage, New York. This here is the Grumman, LEM, or lunar module ascent stage. This, you will see this on later pictures, is the exit hatch through which astronauts, upon landing on the moon, step down onto the lunar surface. This is the descent stage that serves for the landing on the moon, and this upper thing here is the ascent stage for the flight back from the lunar surface to an orbit around the moon. These are the windows through which the astronauts will look out while they are landing on the moon. We'll see all this a little clearer in a later picture. I just wanted to show you here the state in the factory of this kind of equipment. Next slide. Now, after the entire spacecraft has been put on top of the Saturn V and everything has been checked out electrically against the ground consoles in the launch center, which is in this building, the vehicle will be moved out of this hangar and transported to the launch pad about 4 miles away. We are here at the Kennedy Space Center, and VAB stands for Vertical Assembly Building. Now, this is quite a building. It's over 500 feet tall. You may get an idea of the size of the building when you look at the automobiles here. Each of these doors is big enough to slip the entire United Nations building in New York through. And this platform here is about the size of a football field, and this Caterpillar tractor that moves the whole thing at a very slow speed, about 1 nautical miles per hour, to the platform is driven by a 5,000 horsepower diesel. This tower here serves the purpose of providing access to the various stations of the rocket, and at the same time it supports the so-called swing arms. You see some of the swing arms here. These swing arms support, for example, the fueling lines to which the rocket is loaded. It also supports the cables for the signals that are sent into the rocket, and also the cables for the instrumentation data that are fed out of the rocket and displayed in the Launch Control Center. All these swing arms swing out of the way when the motors of the rocket are ignited so that the rocket can clear the tower. Next slide, please. Here you see the Launch Control Center, the inside. Now let me say a word about what's going on here. You have a lot of consoles. For example, these 10 consoles here display important information on the first stage. Information such as how is the pressurization of the tanks coming, are the 4 outer rocket engines that are swivel mounted and used for flight control in the 0 position at takeoff, are all engines in the proper temperature limits and have green light conditions all the way through, do we have electrical power on the power bus, etc. And then you have the same thing for the second stage, and you have the same thing for the third stage, and you have the same thing for the instrument unit, which carries all the guidance and navigation equipment. And then you have the telemeter display panels that get all the data that come out of the rocket to see whether the data are properly received. And then you have additional auxiliary panels for things such as the firefighting equipment on the launch pad, the water controls, and so forth, wind displays. We have strain gauges in the rocket to see whether it takes too much wind gust loads on the pad, things of this nature. Now, as we go up the stairs here, from here upstairs, we have a kind of a rising hierarchy of functions. For example, whereas here 10 panels together make one stage, in this next hierarchy here, you have only 1 man per stage, therefore fewer people. And in this row, you have only 1 man for the entire launch vehicle and 1 other maybe for the spacecraft. But there's a 3rd man here who is in charge of the weather service, and a 4th man for range safety, whether there are any fishing boats in the launch area and so forth. And up here finally sits the launch director, supported by 1 launch vehicle man, where 1 spacecraft man, by 1 man talking to the flight crew, in case it's a manned flight, and by an overall safety man. So you see, there is a reporting channel up here, and very few people, in fact, in the last analysis, 1 man makes the final decision, but unless all this visibility is provided through all these panels, he may make the wrong decision, and for that reason, this Launch Control Center must be so complex. Now, you also note that we are looking at the whole thing from out of a glass cage. This glass cage, and another one on the opposite side, is provided for the unavoidable VIPs, which will always attend such firings, and we just like to keep them out of the traffic pattern. Next slide, please. Well, here our first Saturn V is off. I can tell you this was really a great moment for all of us. We've worked on this thing for 6 years or so. The takeoff weight of this rocket, in fact, all its dimensions are really out of this world. It weighs about 3,000 tons. That's about the weight of a light naval cruiser, or at least a heavy naval destroyer. Its takeoff thrust is 7.5 million pounds, approximately 30% more than the weight. And the takeoff power, as I said, is about 150 million horsepower. Here you see the swing arms getting out of the way. This uppermost swing arm here, by the way, is the arm that will be used by the astronauts when they board the capsule. There's a little white room attached. It not only looks white, but it's really a white room in the sense that is clinically sterile, because we must be very, very careful about contaminating our spacecraft with things like dirt carried in by the shoes of the astronauts. So they leave all this outer garment in this white room and enter a surgically clean spacecraft. There's one little item here that I'd like to point out to you because we won't see it in any of the other pictures. This little tower here is an escape tower. It has exactly the same function of an ejection seat in a military jet aircraft. Should the launch vehicle run in trouble, as indicated on the ground and radioed up to the astronauts by voice communication, or displayed on their own instrument panel, the command pilot, upon advice from the ground or on his own command authority, can decide to abort the flight. He has a switch in his spacecraft. It is commonly known the chicken switch, which fires this rocket here. It's a solid rocket, and which at the same time severs the command module from the lower parts of the Apollo spacecraft. This will then jerk the command module with the 3 men on board with about 20 Gs, a terrific G load, away from the aborting rocket. A moment later, this tower will be jettisoned, and over an established logic sequence, the parachutes will deployed and will be deployed to carry the spacecraft safely to the ground. This then is our escape mechanism. It is useful only up to and including 20 seconds of second stage flight. Any flights thereafter don't need the escape tower, and once we have the third stage under power, we would actually in most cases prefer to abort into orbit. In other words, first going up into orbit in order to enable the crew to time the return a little better at their own convenience, so that they land in the vicinity of a recovery ship. Next slide, please. This is a photograph taken out of our first Saturn V flight shortly after the first stage has been detached. This camera, this is actually a frame out of a color film, shows the Earth here. These are clouds, you see here. And these are the engines of the second stage that you saw in this one picture that I had. And here we are just dropping off the ring with which the second stage is attached with the first one. The first stage is already down here, and about 10 seconds later we drop this ring, and you see this ring just falling through the jets of the second stage. We are approximately 45 miles up in the air at this point, and cruising at a speed of about 8 times the speed of sound. Note that the hydrogen-oxygen jets are completely transparent. You can look right through them as though they weren't any jets at all, and yet you are looking through 1,000,000 pounds of thrust. Only where these jets impinge with this aluminum structure do you see a flame. Here you see nothing. Next slide, please. Well, this is an artist conception taken about 6 minutes later, 6 minutes after the second stage has been fired up. The stage is now also exhausted and dropped off. We are now traveling at about 20 times the speed of sound. The altitude has risen from 40 miles to about 100, and the trajectory has tilted to about an angle of 20 degrees to the local horizon. We fire up the single engine of the third stage. Pyrotechnic cutting devices sever the second from the third stage, and some little retro rockets kick the second stage back to avoid a run-up collision with the third stage. Note these little jets here. These are so-called ullage control rockets. They also burn for a very short period of time. Their sole purpose is to settle the liquid hydrogen at the bottom of the tanks so that the pumps will not inhale pressurization gas instead of fuel. They shut off about a second after these engines are fired up. Next slide, please. Now at this point, our launch operations have been transferred from the Launch Control Center at Cape Kennedy to the so-called Mission Control Center at the Manned Space Flight Center in Houston, Texas. It is this center that controls the entire flight mission from now on to the moon and back to Earth. Just like in aviation traffic control, the tower controller is the man in charge of air traffic in the vicinity of the airport, but when you come out on the open range, you talk to the field service stations. So very much in the same sense, the Mission Control Center takes care of the mission as soon as you're out of the airport control zone. The display on these panels involves all kinds of things. Is the atmosphere breathable in the spacecraft? Is there any contamination maybe in the atmosphere of the spacecraft? Is the temperature all right? What is the remaining fuel reserve for after maybe a corrective power maneuver? How far are we outside of the desired flight path? If a correction maneuver is necessary, how should it be set up? A computer in an adjacent room will be consulted. But there's also medical information. For example, how is the heartbeat of the 3 astronauts? Are there any indication of medical trouble? Are they breathing too heavily? Information of this kind. All these men, you might say, are looking over the astronauts' shoulders, and the so-called CAPCOM, for capsule communicator, normally an astronaut himself, talks to his fellow astronauts in the spacecraft and would say, for instance, we have a reading here of such and such, please read your own instrument and see whether that jibes, or looks like Joe is breathing heavily, anything wrong, this kind of discussion. And this goes all the way on to the trip to the moon and back. Next slide, please. The astronauts themselves can also perform astronomical navigation by looking at star occultations here against the horizon, etc. And they can nail down their approach paths pretty precisely. And when they find out that they're coming in too low or too high, even hours out before they start engaging in the atmosphere, they can start a little thruster movement, just imparting, say, 2.5 foot per second in the upward direction, or 2.5 foot per second in this direction. They can get back into that window. Here again, the similarity between this and an instrument approach of an airplane is striking. The velocities, of course, are a lot higher, but then so are the altitudes involved. And when it comes to times involved, it is amazing. You have hours and hours of available time to nail your approach down more accurately the closer you get. We believe we can nail this down with an accuracy of a mile or two. Next slide. After we know that we are in the proper groove and are re-entering the atmosphere as we should, we will now detach our service module. It is practically depleted. Being in the groove, we don't need propulsion anymore, so we detach our heat-protected command module. We are now rotating it around 180 degrees until it flies with the blunt end forward. Now that is a stylish way of returning from the moon, with the blunt end forward. And the reason is very simple. We are not interested in good aerodynamics in the sense that we would like to get a maximum glide distance. Gee, we came all the way from the moon. We are trying to get rid of our speed, so we are eagerly seeking aerodynamic drag. And we want the drag in such a form that it carries most of the energy, the heat, if you will, away from the spacecraft. And nothing is more effective than a blunt front end, because most of the energy that we have to get rid of is converted into Mach waves, or waves in the air, shock waves that are carried away from the spacecraft, and the heating of the heat shield is minimized. Well, our re-entry begins with 30,000 feet per second. We first go down a bit, then we actually zoom up a little bit again, and then come down in a second dive, but by then we are down to a harmless Mach 15 or so, and then we begin to get rid of the remainder of our supersonic velocity until at an altitude of about 20,000 feet we are ready to deploy our so-called drogue chutes. which will decelerate us further and at the same time avoid tumbling or violent undamped motions of the capsule. And then at a still lower altitude, the pilot chutes for the big chutes will be deployed, and finally the big chutes will follow. Next slide, please. The big chutes, in turn, will be released in steps. There are so-called reefing lines along the periphery, and each reefing line has two so-called pyrotechnic cutters. And this means that at first only a smaller aperture is opened, and when that particular reefing line is cut, the internal pressures, the wind pressure against the chute will inflate the chute to the aperture of the next reefing line until that is cut also. And so we have three different de-reefing steps until finally the whole aperture, the whole diameter of the parachute is deployed. Well, the rest of the descent from about 9,000 feet or so down into the water is pretty much like in Mercury and Gemini. Here again, like in any other things, we have redundancy. For example, if any of these three parachutes fails, we can even land safely in the water on two. The descent will again be in water. Next slide, please. Next slide, please. And the capsule, of course, floats. It will be secured as follows. A first helicopter, hopefully coming down a little more than this one, will go to 6 to 10 feet altitude, from which paradivers will simply jump into the water with scuba gear. And these people will put a flotation collar around the spacecraft to prevent it from shipping water. We may have sprung a leak and we don't want to lose the spacecraft at the end of a trip to the moon, so this flotation collar is pretty important. The astronauts themselves have an option of either staying in the spacecraft and being lifted inside their spacecraft with a big helicopter up onto the carrier deck, or they can be lifted out individually and the spacecraft can then be brought separately. Well, this ends our voyage to the moon. If you still want to bear with me for a few more minutes, I would like to show you a few slides how the technology of this Apollo program can spin back for the benefit of men. Do I still have that time, or would you rather... Okay. So the next slide, please. Our first program in this direction is the establishment of a rudimentary space station in orbit. Here we're using our smaller Saturn 1B vehicle, and we are converting the hydrogen tank, the liquid hydrogen tank of the second stage, into a living room in orbit. Liquid hydrogen has not only the great advantage that it gives us wonderful performance as a fuel, it also has the advantage that when you open a vent valve in outer space and keep it open for a few minutes, the last little bit of hydrogen leaves because it evaporates so readily, and it will leave a surgically clean room behind. There's no odor, no contamination at all, and you can, all you have to do really is pressurize it with air and you can move in. Now, we are building floors, perforated floors, into this tank even while using it for propulsive purposes, and there will be walls inside for compartmentization so that we provide more crew comfort. Up here we will fly in this flight a so-called multiple docking adapter, which, as you will see on the next picture, can be used by approaching other spacecraft to nudge into these docking cones and provide access to the interior of the space station. In other words, this is the railroad station where supply traffic or other astronauts from the Earth will arrive, and there are several such opening cones. There's also an airlock here, so which astronauts can leave from here and go outside for extravehicular operation, or spacewalks, as commonly called. Next slide, please. Here you see what this orbital workshop will look like when in orbit. You see typically the floors here and the crew quarters. Here's our multiple docking adapter. Solar panels previously folded under, for the ascent had been deployed to collect about 9 kilowatts of electrical power to light up and drive the instrument and run the fans in the kitchen and so forth inside this facility. A manned Apollo command service module has arrived in another flight and has docked on to the multiple docking adapter, so that in this combination you now have the living room, the railroad station, a vehicle on which people just arrived, or another crew can return back to Earth. And it can also at the same time be used as a kind of a standby shelter in case some trouble develops here. The guys can always revert back into the command module, either stay in that command module in orbit to check their condition from a safe environment, or just return back to Earth, as the case may be. Next slide. Now, we had to try out under simulated neutral buoyancy or zero gravity conditions what an astronaut can do. There will always be zero gravity in this condition, and all the manipulations, the things that must be worked in this orbital workshop, must first be tried out on the ground to see whether we are asking too much. Now, a very effective technique is to send the man in a spacesuit in a water tank and weigh him down with lead ballast strapped to his legs and so forth, so that he is exactly neutral in buoyancy, and let him perform the work here. We have a great deal of experience now with this technique and find that you can determine quite precisely what kind of a workload it is and how much time is needed to do a certain job under zero gravity effectively. These here are scuba divers, by the way, that stand by only as safety personnel because you are pretty encumbered and clumsy in this spacesuit underwater. Next slide. Next slide. Oh. Yeah. I understand it's going to take a minute or so until the carbon light is trimmed. Well, my next picture shows the interior arrangement within that orbital workshop. In other words, the crew quarters, and particularly the biomedical research equipment that we propose to use here to get a better handle on men's proficiency in the zero gravity environment. We had, as I told you a little earlier, a flight of 2 weeks in Gemini, which is the longest space flight so far made. There were no indications whatsoever that the astronauts were suffering from zero gravity. In fact, the only complaint they really had was that the quarters were so crowded. I remember I talked to Jim Lovell, who was the co-pilot on Gemini 10, after a press conference in which he and Frank Borman talked about this gorgeous experience of flying around the world for two weeks in a Gemini. And I took Jim Lovell in a corner afterwards and asked him, tell me, how is it really for 2 weeks in a Gemini? And his reply was, you've ever been for 2 weeks in a men's room? So crew comfort is essential, particularly if you expect astronauts to do scientific work in outer space. Well, this is the interior arrangement in our temporary space station, the one you saw in the previous picture. You see, for example, a bicycle ergometer arrangement here. Now, here an astronaut will perform certain physical functions. For example, he pedal this thing at various speeds. It has different brake settings here. And he will wear a mask over his head, and the doctors will then analyze precisely how much oxygen he's used up, what his breathing cycle was as a function of the load he was carrying, and also how much CO2 there was in his breath and so forth. They call that ergometer measurements, and it is part of determining the entire body metabolism, but in this case, as I said, under zero gravity. Now this thing here in the distance that looked like a dentist chair is a so-called tilt chair, where an astronaut where his equilibrium sense and its disturbance can be checked careful. The problem here is the following. You have a very sensitive organ in your inner ear. It's called the gravireceptors, and this is normally tuned to 1G. Now, all body mechanisms are arranged in such a way that if the impulses are weakened, then there's an adjustment taking place to increase the sensitivity. For example, at night you can see reasonably well simply because the sensitivity of the eye is greatly increased at night. The little rods suddenly do the functions of the cones, and the iris opens up to a greater f-stop and so forth. So you have the eye adjusts itself to the lower light level. The question now is, what does the gravireceptor do when you put a man in 0G? Could it possibly be that a slight movement of the head puts him at tailspin because he feels it like a terrific sensation, a tremendous departure suddenly from the 0G? We just don't know these things. They must be studied. Now here in the distance you see one of the crew quarters, and I think there's another picture that shows the kitchen. Next slide, please. This will be our first space kitchen. The food will be carried here, but for the first time in the space kitchen we will even serve hot food. It will still be of the add water, mix and bake variety, but it will be undoubtedly better than the kind of food that astronauts had to exist on in the past. Exact control of the food intake is, of course, part of the biomed program. You cannot get good metabolic data unless you know exactly the body intake also. Next slide, please. Well, then I'd like to touch upon one final item shortly. What will we do once we have such a space station, and how can man benefit from this? Now here you see a picture taken from a Gemini spacecraft. You see the spacecraft here in the foreground of the subcontinent of India. This is India here, this is Ceylon, and way back here you can even see the Himalayas. India, as you all know, is a continent particularly badly afflicted with food problems. There's a rapidly growing population, and not only is there already too little food for all the people to eat, but the population grows so rapidly there's also little hope to improve their methods because nobody has enough money to save so that the methods can be improved. Statistics show, moreover, that in India more than 50% of the population is under 15 years of age, which means that fathers already unable to feed their families are absolutely unable to improve their lot or improve the lot for their children, which, however, is so badly needed. Now, what can we do from outer space for people in this predicament? Next slide, please. Look at this chart. In 1960, we had 1.17 acres per man. At that time, the Earth had 3 billion people. In 1970, we will have 3.8 billion people, and we will have 0.92 of an acre of arable soil per head. And now let's go here to 2000. We are going to have 7.4 billion people, and we will have 0.48 of an acre of arable soil per head. Less than 1/2 of what we had in 1960. Now add to this the fact that the worst areas in the world are the ones with the greatest population increase and with this top heaviness in young people unable yet to furnish their own food, particular India and zones in Latin America, here and here. And you see what a problem we have. Now, space can help as follows. Next slide, please. You see here a photograph taken in the infrared with a special emulsion that is not designed to give you the true colors of the terrain overflown, but is designed with the idea in mind of enhancing the contrasts between these various types of crop. When you look closely at this thing, you can see the difference between things like this grayish area is mature lettuce and this greenish area is young lettuce. And you see the difference here again. This is cabbage and this is oats, and peppers and onions and carrots and so forth. The message is, by using such films, and possibly not only one, but 6, 7 different types of films to take simultaneous pictures of the same overflown areas and see how they differ in the various patches, you can get a complete picture on how much crop is being grown and where. That is the beginning of an Earth resources management system, in the sense that we can get a handle on how much crop can be expected during the next harvesting period. But you can do one more thing. You can also determine why is it that, for example, in this patch, stuff isn't growing as well as in this one. Is it maybe that he is using the wrong seed, or is he using the wrong fertilizer, or too little, or is his irrigation method inadequate, or what? Why is it that in India, per se, people harvest only about 20% per acre on what they harvest in the central United States and in Western Europe? Why is it? Well, maybe if we get a better handle on this, we may be able to one fine day give people in these countries advice as to how to improve their own lots, how to use hardier corn, for instance, where the climate is not conducive to the kind of corn they are presently using, or what fertilizers they ought to buy, or how they should irrigate better. I think this kind of an approach to the world food problem is undoubtedly far more promising than endless relief shipments, which not only are resented, but moreover have a way of destroying what little is left of the local agriculture in many of these countries. Now add to this capability others like communication satellites, with which you can establish a worldwide television education system where, for example, people in Swahili language can be taught what to do about it. They can be shown their own pictures. This is your lot here, and if you do this and that, it may help. This could conceivably result for the first time in a worldwide health program that will really be very gratifyingly accepted, because you give everybody the convenience of a little switch on his television receiver. If he doesn't want to hear it, he can turn it off. Chances are, however, that they will not turn it off. The United States just concluded a few weeks ago the first cooperative agreement with Mexico and Brazil on the technique of surveying Earth resources in these two countries. And they are not only limited to food crops, but also to things like, they include things like cotton, and they also include mineral prospecting. Similar techniques can very well be used to find out in what mountain ranges it may be promising to look for copper or for tin, or where it may be promising to drill for oil. The next slide shows another application. Here is a picture taken with a handheld camera out of Gemini that shows you a forest fire in Florida. In fact, 2 of them. Now, forest fires also damage a great deal of timber all over the world, and forest is undoubtedly a resource as important as food. We have made similar studies with respect to tree health. For example, you can photograph from orbit, believe it or not, a forest area, and you can distinguish healthy areas where the trees are coming along well, and afflicted areas where, for example, bugs and other tree diseases are destroying the timber. Pictures of this kind produce information that even a forest ranger walking through the very woods can never get. He may know that some of the trees seem to be sick, but to draw a line clearly how far the disease has been spread and where, for example, DDT spraying planes should go in to stop further spreading of the disease is unknown and virtually impossible today. Now, the same equipment that looks for crop can therefore also look for forest fires and tree diseases. Next slide, please. Well, another application of our first orbital workshop will be a solar observatory, and here our by now well-known cluster with the command module will be joined by a manned solar observatory. We are presently building this thing also in Huntsville. It has its own power supply, these windmill-type surfaces, providing additional power to this. With this solar observatory, we shall investigate the sun, not in the light just of visible light and a little bit of infrared, which is really the whole region in which the sun is known, but we will study the sun predominantly in the light of such radiation for which the Earth's atmosphere is opaque. There is far ultraviolet and X-ray and gamma rays. We have some of the finest solar observers in the United States in this program. In fact, there was quite a competition on before the most valuable experiments were selected. And lest you think that we in NASA think we have all the wisdom and can tell some Nobel Prize winners as to who has a better idea than which other Nobel Prize winner, we have a five-star committee that does these selections, and unless that five-star committee sprinkles its holy water on these various experiments, we just don't fly them. My last slide shows what this what we are looking for on the sun. You see typical sunspots here. This is a photograph of the sun taken in the light of the so-called hydrogen alpha line, which is an ultraviolet in the ultraviolet region. It is the basic line of the hydrogen series, and you could not take such a picture from the surface of the Earth. This was taken with a simple rocket that just stayed above the atmosphere for a few minutes. Its resolution is, of course, very poor. What we are proposing to do with our manned observatory is to blow up a small area like this to the size of this entire screen and really see what's going on and what energy phenomena are occurring around solar flares and solar sunspots in the light of this kind of radiation for which the Earth's atmosphere is opaque. Well, why are we doing this thing? Well, I think this is a typical example again where we are just plainly satisfying our curiosity, but since the sun is the giver of all life on Earth, it stands to reason that if we understand the mechanism of what makes the sun tick a little better, men will undoubtedly benefit from this. One fine day will lead to better weather forecasts and to a better understanding of the entire energy transfer mechanism between Earth and Sun. Well, thanks so much. This ends my presentation.